Good morning. It's a great pleasure and privilege to be here today. Let me start, if I may, by telling a story. This is a story not written by me, but a story written by Jorge Luis Borges, the Argentinian poet and novelist, who wrote a short story, a very famous short story, it's only one paragraph long, about an ancient lost kingdom, which was obsessed with cartography. And the aristocrats of this kingdom cast one map after another of progressing levels of ambition until they launched the ultimate mapping project, which was to create a map of their kingdom on a scale of 1:1. And in Borges' story, the fragments of this failed effort to create a map that was the same size as the kingdom can be found rotting in the corners of this lost empire. And that is the end of the story. It's exactly one paragraph long, and it's obviously a classic Borges story. It's full of metaphysics, it's full of thoughts about the nature of thought and the nature of human ambition. What I want to suggest to you in my brief remarks this morning is that that image of Borges' map, a map on a scale of 1:1, a map that is the same size as the reality that it represents, is in fact the image that we should have in our heads when we think about where technology is taking us. And to make the point, let me share with you some examples. First, this is what the Google car sees. You're aware of the Google self-driving car. In the inset, you see what would be seen by a camera on the dashboard, and the larger picture shows you what the car is aware of. And as you can see, it's aware of roads, it's aware of traffic lanes, it's aware of signals, it's aware of other traffic, it's even aware of pedestrians and cyclists. In just a moment, you will see the car trying to overtake a typical Northern Californian cyclist who, of course, can't make up his mind whether he's turning left, turning right, which lane he's in. It's typical suicidal behavior, but the car successfully navigates around the hazard. In fact, the Google car has only had 2 accidents in its history, one of which was when somebody rammed it from the rear while it was parked, and the other was when it was being driven manually by a Google engineer. So this is not wildly futuristic technology. Within 3 or 4 years, these cars will actually be on the roads. Seriously, they will be on the roads in a few years. But that's not the only way that the world can become self-aware and self-mapping. Consider this, still on the theme of transportation. This is a car park, or parking lot, as Americans would say. The significant thing about it is that the parking lot is aware of the vacancy of the parking spaces. There is a small sensor, costs about $25. It has a battery in it that lasts about 5 years. It has a low-powered radio. And these sensors form a mesh network, which basically mean that the municipality, in this case, which has invested in this very cheap technology, is able to use these sensors basically to collect parking fines when somebody outstays their welcome. But the extensions of this technology are very obvious. For example, cars themselves are acquiring near-field communication technology. It only costs a few dollars. So the NFC in the car can communicate with the sensor in the parking space, and you can pay your parking fee automatically. If the owner of the car park knows the availability of parking spaces, he, she, or it can broadcast that fact to the world. 40% of the traffic in any major city is people driving around in circles looking for parking spaces. If where the parking space is can be known beforehand, if, for example, you can book it, if it's raining and the price, like Uber cars, doubles and you simply auction off the parking space, you can massively improve the efficiency with which these spaces are allocated. And then finally, of course, very obviously, in the day when the Google car finally drives you to work, after it drops you off, the car can go off and find a parking space for itself. Again, you see the key point here, that the world, the actual physical distribution of cars in spaces on asphalt, and the map of the world, the electronic rendering of what is going on, become coincident. Or consider a third example, which in many ways is perhaps the most dramatic one, the map of ourselves. The nature's map is the chemical structure of DNA. And it took something of the order of 10 years and over $150 million to map the human genome. What's happened in the intervening years since the first genome was completed is that the cost of mapping the human genome has come down with extraordinary speed, to the point where within about a year or so, we will be able to map the human genome for less than $100. Now, when mapping the human genome costs $150 million, it becomes a very expensive exercise in big science. You are essentially assuming away all the variation in human genomics. You're looking at a single abstracted thing called the human genome, and you are, as a scientist, are trying to understand things about it, which is one tremendously heroic scientific breakthrough. But when genomic mapping takes 20 minutes, $99 while you wait, it's no longer a matter of abstract research, it's a matter of clinical medicine. And when you go to the doctor in just a few years' time, the first thing the doctor will do, if they haven't done so already, will be to map your genome. And the essence of medical practice will then become relating this fundamentally statistical characterization of your unique human characteristics with your medical record, with your symptoms, with ambient data from the environment, if you're asthmatic or have some condition of diabetic, some condition of that form, in order to come up with diagnosis and treatment. Essentially, what used to be a hierarchical, a process based on expertise, conducted within hierarchical organizations, where the final judgment was made by somebody with many, many years of extremely expensive technical training, increasingly becomes a statistical exercise. Already, Watson, the software technology developed by IBM originally to win the Jeopardy contest in the United States, which it famously did a couple of years ago, Watson is being applied to the task of medical diagnosis. And it turns out that using purely statistical techniques, Watson is able to combine all of these data sets, including genomic data, and outperform 98% of human medical practitioners. So this, in some very, very fundamental ways, is the direction that medicine is going. It doesn't render the doctor obsolete, of course, but what it does do is fundamentally transform how we need to think about medicine. In particular, what it means is that our ability to aggregate, to standardize, to anonymize, and to protect large data sets about, for example, genomic information, becomes really key to our ability to use these kinds of methods, fundamentally statistical methods, in order to address these kinds of problems. This is the challenge. It's a challenge in terms of the computer science and the mathematics and the science, but it's also a challenge in terms of the institutions. In countries like the United States, where medicine is privatized, each hospital, each clinic thinks of medical data as being proprietary. It's a switching cost. It's a source of what they would call competitive advantage, all of which makes this kind of science, this kind of medicine, completely impossible. So we have a fundamental conflict emerging between the direction that the technology is taking us and many of the institutional arrangements which in the public sector as well as the private sector stand in the way. And that is destined to become an enormous challenge over the next 10 years. Or consider one last example of how data can serve as infrastructure. You're all familiar, I'm sure, with maps like this, where the way the United States looks at night, where you can see the cities and the roads and so forth in the darkness. If you do the same kind of map for Africa, tragically, it is the dark continent. The lack of infrastructure is one of the things that holds back economic development. But, a very interesting story. In the Ivory Coast, Orange, the French telecommunications company, is the monopoly provider of cell phone services. And about 2 years ago, they launched a project where they collected metadata on cellular phone usage for just about the entire population of the country over a 9-month period, an immense data set. They again very carefully anonymized it to make sure there was no issue about what anybody said or who any individual talked to could be extracted from the data, but they published the data set. And they said, essentially, to the world's researchers, the world's academics, go at it, see what you can find in this data. And there were a total of 81 research papers that were written exploiting this really rather extraordinary data set to see what kind of patterns could be seen. Some of this research was actually rather obvious, the kind of thing maybe you and I would think about if we pondered it. For example, researchers realized that because the cell phone registers with a tower, what it's providing you with is a map of how people move around. And that's basically the pattern that you see on the left in a highly simplified form. For the entire population of the country over an entire 9-month period. We're talking about a very large data set. On the right, you have the pattern of how people communicate. Who talks to whom? Now, the interesting thing is, if you are, say, an epidemiologist or you're a public health official, and your concern is with the spread of infectious diseases, the map on the left essentially is the map through which the disease spreads, because it's through physical movement. The map on the right is how various countermeasures, which are essentially often propaganda, word of mouth being the most powerful way of changing people's behavior, that is the pattern of word of mouth. So what you have from the same underlying set of data is both the map of how the enemy moves, namely the disease, and the map of how our countermeasures can move to try to head it off. And these techniques are actually being used today by the World Health Organization, by the Gates Foundation, actually interestingly working with the Boston Consulting Group, to combat Ebola in West Africa. But that is an obvious application, at least in the abstract. I mean, the complexities of doing it are serious, but the idea might occur to quite a lot of us. This one is a little less obvious. Some researchers at IBM in Dublin realized that this self-same data set showed the commuter patterns in cities. So they took the largest city, Abidjan, and they extracted from the data the daily movements of people from their home to their workplace and back. Why? Because the cell phone is registering with different towers. They then asked themselves the question, what is the optimal design of a bus system, given that you have this pattern of hundreds of thousands of people moving around the city on a daily basis? Mathematically, it's a trivial problem. It's an integer programming problem. In computational terms, of course, it's very difficult because you're talking about immense data sets. They set up what's called a Hadoop cluster. They ran this Hadoop cluster for 4 days to solve the problem, and they got a solution. It turned out that the solution was able to reduce by 10% the average commuting times in Abidjan without adding a single bus. So for the cost of a couple of months of research by a few PhDs, plus 4 days of running a Hadoop cluster, they were able to have what is, when you think about it, an extraordinary impact on the effective GDP per capita of people in this city. Now, again, notice the really interesting thing about this. What's happening here is that the data is serving as infrastructure. This data about how people use cell phones in a society where other kinds of infrastructure are so completely absent, turns out to be a source on the basis of which all sorts of insights can be had that could not have been known by anybody, in particular could not have been known by the phone company before the release of the data. So we have a new paradigm here. We have this idea that data ceases to be the byproduct of linear processes. We do something and we get information from the fact that we did it, and we use that information in order to do it better. That ceases to be the model of how data gets used. Instead, the way we need to think about data is this massive aggregation for purposes that are open-ended and unknowable before the fact, making possible all sorts of experimentation, innovation, technical improvements in things like commuting times that could not have been anticipated before the fact. It's interesting again to observe that Orange did this in the Ivory Coast, where they are the monopoly provider. They would never do it in France. Why wouldn't they do it in France? Because they don't want that data to go to their competitor. So again, you have a fundamental issue about the compatibility of our institutional arrangements in a governmental organization, or compatibility of our departmental organizational structures with the possibility of this kind of data exploitation. So what's the larger pattern here? The larger pattern here, I think, is the fourfold interaction of big trends. And each of these trends individually, I think we're quite familiar with. The really important thing is the way they multiply each other. The first is what people call the Internet of Things, the proliferation of sensors, things like those $25 devices implanted in the parking spaces. Current estimates are, in fact, I saw an estimate just a few days ago, that by the year 2030 there will be something of the order of 100 trillion sensors in the world. The exact number doesn't matter. What does matter is the simple fact that sensors are becoming so cheap and so ubiquitous. There are already in the world today 140 sensors for every man, woman, and child on the planet. That's the situation today. As their price comes down and their proliferation goes up, every single product becomes aware. It becomes able to know its own status and report its own status. And therefore, in some very, very profound sense, it ceases to be a product and it becomes a service. Secondly, what happens to all that data? Well, it accumulates, and the accumulation of the data is resulting in this extraordinary growth in the world's stock of information. You've probably seen the statistic that the world's stock of information now is doubling every 2 years. That's the phenomenon, of course, of big data. But data in itself doesn't help us very much. We need insight. We need to understand and see the patterns in the data. And this is the third big change that is happening. I like to call it sense-making, but there's various terms that get used for this. The key point is very simple, that there has been a revolution in statistical technique in just really the last 10 years, as statisticians have turned to addressing problems of computation when the data sets are very, very large, to the tune of billions of rows and columns of numbers. And it turns out that there are very, very special issues that arise in this context, and it results in a fundamental shift in technique, away from classical statistics towards what technically you would call Bayesian statistics, where you have a guess, and then you get more data, and you improve the guess, and therefore you algorithmically pursue the answer, but you never actually get there, towards substituting correlation models for causal models. You don't need to have the same degree of abstract problem formulation. You just let the data speak for itself, and so forth. And then the fourth big trend is mobility. Mobility is important because the number of cell phones in the world is now roughly equal to the number of people, because an increasing fraction of those, of course, are smartphones, because they are themselves sensors feeding data into the network. They are a source of information, but also they are a means by which insight can be consumed. You used to have to go somewhere to get insight. You went to something called a library to do a search, right? Nowadays, you can do a search from your phone. You can even do a search from your watch. So increasingly what's happening is that the insight is delivered at exactly the point where it is needed. It doesn't become a separate exercise to go somewhere and get the insight. Again, all part of this fundamental shift to the world becoming self-aware, the world becoming self-describing. Now, the other key thing to emphasize about this is that these are really recent phenomena. If you turn the clock back 10 years, hardly anybody had identified any of these four trends. These are really, really recent things. And the fact that they are mutually multiplying, that they reinforce each other, is what creates this tsunami of transformation, excuse me, this transformation in what it is that we can do with information. Now, what therefore is the architecture by which we can exploit this? How do we organize to do this, whether it's in the private sector or the public sector? Well, the best way to see that is to look at a pure example of a company that has grown up in this world, and the example I'm going to take rather obviously is Google. The interesting thing about the way the Google search algorithm operates through Google's system is that it has this stacked and layered architecture. You can think of each of these boxes as being a server, and when I do a query, that query gets passed down through these various layers of capability. It gets broken into its component pieces, and it ends up in these servers at the bottom, which are called index servers, each of which contains essentially a list of every instance on the internet of a particular word. Those lists are returned, they are sorted in accordance with various algorithms. There's then a second search which pulls up the so-called snippets, the examples of how the information is being used. That comes back, it gets aggregated, sent back through the server system, and returned to me in a quarter of a second. An absolute miracle of technical architecture. Now, notice a couple of things about this. First of all, it is modular. It's divided into little pieces, and the little pieces are designed and operated separately. Modularization is key to how we deal with complexity. Secondly, it is layered. Each of these rows represents a different kind of functionality. What's at the bottom essentially is infrastructure. Those 2.5 million, literally 2.5 million servers that do nothing but hold lists of words sitting at the bottom of the architecture. At the top, you have something that faces the customer, that is the front end of the Google system. And that layered architecture is really fundamental because it enables Google to implement something which engineers call the end-to-end principle. The end-to-end principle is the idea that what you do is you move functions as far up this stack, as they call it. You move these functions as far up the stack as you can, as is consistent with their efficient utilization. So therefore, if something needs to be customized, if it's experimental, if it's something where you're recombining resources, you move it as near to the top as possible. If, on the other hand, it's infrastructure, it is a list, it is a passive resource, then you move it as low in the infrastructure as possible. And that end-to-end principle enables Google, and in fact this is the architecture of the entire internet itself, it enables the internet itself to finesse this fundamental organizational trade-off between efficiency and scale. You get scale at the bottom, I'm sorry, I misstated that, the fundamental trade-off between innovation and scale. You get scale, efficiency, utilization of capital-intensive functions at the bottom of the stack, and you get experimentation and innovation at the top. And by separating those two kinds of activities out, a fundamentally different generative architecture is created, which is able simultaneously to scale massively and also to be highly experimental. So if Google doubles in size, they can add another 2.5 million servers at the bottom of this architecture with no problem whatsoever. Scalability at the bottom is essentially unbounded. And once Google has the architecture in place, if they want to introduce new products, they get what economists would call economies of scope, the ability to add new things at the top of the stack by simply recombining the same resources into new products and services. So they add products and services at the top, and they add scale, data, volume at the bottom. Now, at the top of the stack, what that enables is innovation. The innovation isn't necessarily done by Google itself or by any provider. It can be done by customers. In fact, one of the interesting stories of the last 10 years has been the way that so much innovation has come from users themselves. I won't go through the details of this story, but very briefly, an engineer called Paul Rademacher needed to move his home to San Francisco, and he found himself going back and forth between Google Maps and Craigslist in order to try and find a place to live. He had the idea of hacking into the JavaScript that these two internet sites used to deliver their information and creating a synthesis. And that synthesis is called a mashup. And the one that he created looked like this. It became a business in its own right. It's called housingmaps.com. What he had created was the first real estate search engine. And all he was doing was combining these two different resources into a new thing that created this one-to-one map. Again, you see the theme recurring, one-to-one map relating the reality as it was categorized with the reality as it is on the ground. Now, Google got wind that Rademacher was doing this. He'd started a business, he was getting hundreds of thousands of hits. Their first instinct, of course, was to sue him and put him out of business. Their second instinct was to hire him. And they hired him to create APIs, application programming interfaces, the first of which was for Google Maps. And Google, in fact, has published something of the order of 150 APIs that are essentially simple hooks that enable anybody with very limited programming skills to take Google data sources and use them in their own applications. It turns out that there's actually something like 10,000 APIs that have been published by hundreds of companies on the internet, collectively creating, when you think about it, the possibility of 10,000 squared mashups, right? 10,000 squared combinations of any two APIs. Most of those, of course, are meaningless and stupid, but there are actually 8,000 of these mashup businesses that exist. The interesting thing about them isn't that any one mashup is a tremendously radical thing. I mean, if you go back to housingmaps.com, I mean, yes, it's very nice, but this is hardly an earth-shattering innovation. The key point is that if you did something like that 10 years ago, not only did you need extremely sophisticated programming skills, but you needed the investment of months of work, and therefore you needed funding, you needed a business plan, you needed to get a venture capitalist to sponsor this, etc., etc. The barriers to doing this were huge. Today, exactly the same thing, thanks to ABIs, can be done in a few hours. And so the time, the investment that's required for innovation goes through the floor. And when the investment required goes through the floor, then the possibility of how innovation happens and even the motivations for innovation can change. It turns out a lot of these 8,000 APIs aren't businesses at all. They're things that people did for the fun of it. They're things that somebody did because they wanted to show how smart they were. They're things people did for ideological reasons or for humanistic reasons or what have you. When the cost of innovation is just one wet Sunday afternoon's worth of work, then the models by which innovation happen fundamentally change. You don't need corporations. Frankly, you don't need government departments. You don't need venture capital even, because people can and will do it for themselves if the architecture is so designed as to make it possible. That's just one architecture of how innovation happens at the top of the stack. There's many others. For example, e-lancing, Uber. Think about Uber. Think about Airbnb, a platform which enables people to buy and sell services. Think about a commons like Wikipedia. Think about developer communities such as the Apple iPhone and Android community. Think about social networks. Think about peer-to-peer networks such as BitTorrent. Or Bitcoin, which obviously raises profound issues about the nature of who controls the money supply. All of these phenomena proliferate and flourish at the top of the stack. Why? Because all of the scale has been drained out at the bottom. So, if I could sort of just briefly try to summarize what the key points are. What's emerging is a new architecture. It's fundamentally horizontal. At the bottom, we have data serving as infrastructure. At the top, we have distributed communities within which innovation takes place. And we have these fundamentally different design principles associated with the different layers in between. What it amounts to, therefore, is, I think, 6 headline propositions. The first is this phenomenon of the convergence of these big 4 forces: sense-making, big data, the proliferation of sensors, and mobility. And those 4 things together are what create this self-describing world. Secondly, products become services, services become systems. Thirdly, data processing becomes infrastructure. Because of the scale involved, we have cloud computing. More importantly, and less obviously, data itself becomes infrastructure. Data becomes something that we build, we release, and we allow the world to exploit as it chooses. We see the emergence of new topologies of experimentation, innovation, and customization at very, very small scale by very, very large numbers of people. And we see the emergence of horizontal architectures, stacks, and platforms replacing the traditional vertical architectures, which in the business world we would call value chains, in the bureaucratic world we would call departmental organizations. So the world gets repolarized from being essentially vertical to being essentially horizontal. And the managerial challenges that we all face, whether it's in the private sector or the public sector, are to grasp the scale, the enormity, and the impact of this kind of change, and find ways to apply that in the contexts where we have the ability to use information in fundamentally new ways. Thank you very much.